If you had a $17,000 watch, would you throw it away after just a couple years of use? Obviously not. You'd keep that thing forever. And if you did decide that you wanted to get rid of it, you'd probably sell it to someone else to try to make some money off it. And they would then sell it to another customer, or they might try to melt it down to get the materials back. A very logical thought process, right? Unfortunately, this is the exact opposite of what is happening in the battery industry today. So 1 ton of battery-grade lithium costs $17,000. But once this is used in a battery one time, it most likely ends up in a landfill. A landfill is a terrible place for it for a bunch of reasons. Not only are you throwing away $17,000 per ton, but this discarded battery can also have a bunch of environmental and economic impacts. So first off, landfill fires. In the UK alone, landfill fires cost the economy 158 million euros per year. And almost half of these fires are caused by lithium-ion batteries. In terms of environmental impacts, these batteries have a bunch of toxic chemicals in them, and when you put them in a landfill, these chemicals can leach out into our soil and water, polluting it. To make all of that even worse, the amount of battery waste we have is expected to grow exponentially, and this is due to the increasing popularity of things like EVs and electronics. But the IEA predicts that by 2030, we're going to have 145 million EVs on the road. That is a lot of batteries, but the thing is, we don't have anything to do about the battery waste. There are a ton of ways we could go about solving this problem, but the one that I'm super interested in is increasing the lifespan of batteries. So let me break down my logic. Car batteries last about 7 to 10 years, and phone batteries last about 1 to 5 years. If each of these batteries lasted longer, then we technically need less overall batteries, and that means less overall battery waste. The reason why this whole battery waste thing is such a big problem is because we can't really recycle the battery. And the reason why we can't recycle them really is because it's uneconomical to do so. So nobody really wants to put money into something that they're going to lose money on. To make it economical, we essentially need to solve the bottleneck of battery disassembly. When you want to recycle a battery, you have to break it down from a battery pack into the individual cells. And then you need to break down those cells into the actual materials that make them up. So this would be the lithium, the aluminum, that sort of thing. But the problem is that batteries are literally cemented together. In a battery pack, there are a bunch of cells and they're like quite literally cemented together. So disassembling them is just about impossible. To reduce this hurdle that we have to battery recycling, we'd essentially need to entirely redo the way that batteries are made. And that's a really big ask that probably won't happen for a while, because batteries are made that way because it's the most economical and the most efficient. That's why I think we should focus on increasing the lifespan instead, so we can reduce the battery waste, and as opposed to trying to improve the recycling process, because it's a lot more feasible and it would probably happen a lot sooner. There's a way that we can extend the lifespan of batteries that doesn't require new materials, and it doesn't require expensive research and development. The technology already exists. Before I tell you about it, I'm first going to have to explain why batteries age. And the main overarching reason is because they're used under harsh conditions. So they get too hot, they get too cold, they're overcharged, over discharged. So when this battery is operated outside of the ideal conditions that the manufacturer has designed, it ages faster. So if it was operated only inside its ideal ranges and it wasn't operated under harsh conditions, then it could last about 20 to 50% longer than it currently does. 20 to 50% just by changing the way we use it. Like, why are we not doing this? But the even better bit is that a software literally already exists to do that, and it's called a battery management system. So essentially, like I mentioned, it's a software that keeps the battery inside its ideal operating range, and this can help to increase the lifespan, increase the performance, and increase the safety of these batteries. And I've got an article that I linked down below, and it talks all about BMS and how they work. But in this video, we're going to dive deep into the aging mechanisms to better understand how exactly battery management systems can help to slow down the aging process and increase the lifespan of batteries. For our battery management system, or our BMS, to properly prevent battery aging, it needs to first understand what is causing battery aging in the first place. And then it needs to counteract those factors. So I've broken it down into 3 main categories: corrosion, increased impedance, and dendrite formation. And we're going to dive deep into what these are, why they happen, and how we can prevent them. Let's start with corrosion. So corrosion can essentially be summarized as unwanted chemical reactions. And at the base of it, what's happening is that the electrolyte is reacting with the metal components of the battery, so the electrodes and the current collectors, and it's forming hydroxides and oxides. The reason this is bad is because when these two things react, some of them get consumed to form the new product. That means that when this current collector reacts with the electrolyte, some of the current collector is going to be taken away. And that means I'm going to have a hole in the current collector, which means that the electricity can't flow properly, which kind of impairs the function of the battery. This also increases internal resistance, which we're going to talk about later. So the main problem is that we are eating up components of the battery that we still need to be used. There are a couple of battery use cases that can cause this corrosion to happen faster or happen more often. So the first one is going to be overcharging. So the problem with overcharging is that it means that there's a higher voltage potential in the battery because you're putting more electricity into it, more energy into it. And this can actually cause the electrolyte to break down. And when the electrolyte breaks down, the byproducts that it forms can actually react with the metal components of the battery and then corrode them. The second thing that can cause corrosion to happen more often and faster is going to be over discharging. So the problem with over discharging is that it can lead to dendrite formation. We're going to dive deeper into this, but as it relates to corrosion, essentially what is happening is that there's fresh lithium metal exposed to the electrolyte. So the electrolyte is going to react and it's going to corrode that lithium metal. And while that lithium metal isn't necessary to the function of the battery, it's still bad because essentially when two things react, right, some of the electrolyte is also going to be consumed. So that means that we're going to have less electrolyte. And that's bad because the electrolyte is the main source of ion conductivity inside the battery. If we have less electrolyte, we essentially have less ion mobility, and that can affect the battery capacity. And the third factor that can increase corrosion is the temperature. So higher temperatures are going to accelerate corrosion. And why this happens is because at higher temperatures, molecules have more energy. So that means that they can move faster. And that means that these corrosion reactions can happen faster. One of the ways to prevent corrosion, other than avoiding those three things that I just mentioned, is to employ something called passivation layers. So passivation layers are essentially these films that will form on different components of the battery. So specifically the electrode and current collectors. And they'll kind of act like a shield to protect the battery from corrosion. And these will kind of form naturally. And this actually leads me to my next point, which is going to be increased impedance. So impedance is essentially the resistance of a battery to current. So increased resistance means that there's more energy that's going to be lost, and so the efficiency is going to go down. But passivation layers actually increase the impedance. And I know, I just said that passivation layers are really good for preventing corrosion. But in the battery world, you have to make a lot of trade-offs. And this is one of them. So if you want to prevent corrosion, you're going to need passivation layers. But these passivation layers are going to increase the internal resistance of the battery and therefore the impedance. Which one you choose to prioritize is going to depend on the application of your battery and then which properties you're going to care the most about. But back to impedance. So oddly enough, corrosion also increases impedance. You see how connected these things are? So when I was mentioning that corrosion is going to eat away at our current collectors, that means that electricity is not going to be able to flow as well through that battery and therefore increase impedance. The main driver behind increased impedance is increased internal resistance. So extreme temperatures can increase internal resistance. And this is because both high and low temperatures can increase electrolyte viscosity. And electrolyte is essentially the thing that carries the ions between the anode and the cathode. So it essentially allows for ion movement. And when the electrolyte is more viscous, that means that it's not able to move as well. So therefore the ion mobility goes down, and then performance will also go down. Temperature is one of the biggest factors in battery aging, as you can see from this graph. Another point I want to mention is that when these passivation layers become uneven, so for example, one area is a little bit thicker than the other areas, then that can increase the localized resistance. And this can result in the internal resistance of the whole battery increasing as well. So to prevent these passivation layers and increase impedance from forming, what we want to do is we want to just prevent corrosion and then keep the battery inside its ideal temperature range. But it's important to note that there probably is going to be a lot of trade-offs that need to be made as the conflict between passivation layers and corrosion. The last battery aging mechanism that I want to talk about is dendrite formation. So dendrites are essentially these long needle-like structures that will grow, and they're going to grow towards the center of the battery. This means that they could potentially pierce the separator, which means that the anode and the cathode would be separating, and this could lead to short circuiting and then thermal runaway, which looks like this. So it's essentially an explosion, and it's definitely not what we want. The main reason for dendrite formation is uneven deposition of lithium during cycling. So let me explain what I mean. The way a battery works is that you have your lithium atom, and this lithium atom has 3 electrons. The outermost electron is called the valence electron, and it can be detached really easily. So essentially what happens is you have your atom and your 1 electron on it. That electron will go away, so now this is a lithium ion. They will move through the battery, so the ion is moving through the battery, but the lone electron is moving through an external circuit. This is what we want because then we can harness that electron's movement as current, which can be turned into electricity. So that's essentially how the battery works. But the problem is that when these lithium ions are moving from the anode to the cathode or the cathode to the anode, they won't necessarily diffuse all throughout the cathode or the anode evenly. So there might be like a lot of lithium ions at the top and not very many at the bottom, for example. The problem with this is that means that there's a higher concentration of lithium at the top and a very low one at the bottom. So when you have a higher concentration in a certain part of this battery, then that means that the solution will become oversaturated. So there's going to be too much lithium per unit volume of like electrolyte in this case. And that means that the solution is going to be oversaturated. And that means that the lithium will precipitate out. So it'll go from being a lithium ion back to being a lithium metal. So that's with its 3 electrons. And this is bad because when you get metallic lithium forming inside a battery, it's going to deposit on the surface and it's going to just like accumulate over time because this is an irreversible process. And that's why we see those dendrites form. The really interesting thing about this though is that uneven lithium deposition only happens during these harsh conditions. So overcharging, overdischarging, and high temperature. That is the only scenario in which uneven lithium deposition happens. I mentioned that lithium is going to essentially go from being an ion form to being in metallic form, and that means that it would have gained an electron and then been reduced. So that is also an essential part of battery function, right? So what's the difference? The problem with lithium being reduced and forming dendrites is that reduction of lithium is happening at a very uncontrolled or fast rate, and it's going to accumulate and form those dendrites. There's one more thing I want to mention about dendrite formation. So not all lithium deposition is bad. There are 3 different types: mossy, granular, and dendritic. The first 2, mossy and granular, are actually quite good for battery function. And the reason for this is because they essentially prevent dendrite formation, which is amazing. And the reason they do that is because the way that they accumulate on the surface is that they're very porous in nature. So it's really hard for dendrites to grow on top. But lithium dendritic formation is bad because it's what causes these dendrites to form. And those harsh conditions that I mentioned a bit earlier, so overcharging, overdischarging, and temperature, those can actually accelerate the formation of dendrite. So one way to prevent lithium deposition, specifically in the dendritic form, is to use pulse charging. And this essentially means that instead of just delivering a constant voltage to your battery, you deliver a little bit and then you pause. And you deliver a little bit more and then you pause. And specifically, you want to use shorter pulses with longer durations in between. And what this will do is it'll allow the lithium ions that have been moved from, say, the cathode to the anode, and it'll allow them to fully disperse all throughout the anode, so that we don't get that accumulation. The other way that you want to decrease lithium dendritic formation is to keep the battery inside its ideal temperature, because if the battery gets too hot, then that means that there's going to be more energy for the molecules. And then that means that the lithium ions are going to move faster, so they're going to have more mobility. And that just enhances the problem of uneven deposition. As a TLDR, we broke it down into the 3 main aging mechanisms. So corrosion, which is essentially summarized as unwanted chemical reactions, and then increased impedance, which is increased internal resistance. And the last one is going to be dendrite formation. And dendrite formation is caused by uneven deposition of lithium. So those are, I think, the 3 main aging mechanisms that causes batteries to age a lot faster than they should be, and results in us throwing away batteries sooner than we should be, and then having more battery waste that causes all these terrible effects. So going forward, I'm going to see how we can use BMS to counteract these aging mechanisms and make these batteries last longer. Thank you so much for watching. I really do hope you learned something, and have an amazing rest of your day. I'll see you in the next one.